Hello everyone, welcome to another video lecture in trigonometry, another partial video lecture because today we are completing the Law of Cosines for my students at the University of South Florida. The goals for this video are actually pretty, I would say, achievable in a short period of time. We're going to just remind everybody of the basics to make sure that we all have the formulas in front of us that we need. We are going to do several exercises, including some things I wasn't able to cover in class, and then we should be done. So let's go ahead and pile right on in. Now, when I'm talking about the law of cosines, I usually draw one of the two pictures that you can see on the right here. You'll notice that in this picture, I'm really only interested to begin with in a single angle, theta, which I usually put at the bottom left-hand corner. There are going to be two sides adjacent to that angle, so I call them adjacent 1 and adjacent 2. Not because I lack imagination, hopefully I don't, but because it makes it easier to explain where the pieces go in my formulas later. And then the side opposite I label as op. When I have sides adjacent 1, adjacent 2, and op, and an angle theta, which is opposite the side opposite, then I can write the formula opposite length squared is equal to the sums of the squares of the adjacent lengths minus 2 times adjacent length 1 times adjacent length 2 times the cosine of the angle between them. If you're looking at this formula and thinking to yourself, wow, that first line looks a lot like the Pythagorean theorem, you are not wrong. This is actually an extension of the Pythagorean theorem. The Pythagorean theorem would require that the angle theta in my pictures is a right triangle. If you have that happen, because cosine of 90 degrees is 0, this bottom line here would disappear, and we would simply get the regular old Pythagorean theorem. By adding in this last term, which I typically call an error term, we adjust for the fact that the angles may not have a right angle anywhere in them. And then we're able to do a lot of the same work, but in a more general setting. There is also a way we can manipulate this formula that we have right here, and we can use what we've written to figure out the angle theta. This formulation right now that we have in front of us is best for figuring out the lengths of one of the sides if it's missing. So for example, if I don't know the length of the side opposite, this formula would give it to us. If I knew one of the adjacent sides but not the other, as long as I had the side opposite, the one adjacent side, and then the angle, I'd be able to use this formula to get the other adjacent side. But if I want to get the angle theta, so I know all three sides, but I don't know the angle theta between adjacent 1 and adjacent 2, I would need a formula that looks more or less like this. So, simply using algebra to move everything to the opposite side of the equation except for cosine of theta, and then taking arc cosine of both sides, I wind up with one of two ways of writing this. In class, what I did is I kept things simple, and I said, well, when I take arc cosine of both sides, I'm going to wind up with something like arc cosine of the opposite squared minus the two squares of the adjacent side lengths divided by negative 2 adjacent 1 adjacent 2. That's a little bit messy, so I recommend that if you have practiced doing this and you're pretty comfortable with getting the angle using arc cosine, rewrite the inside just a little bit. Then it becomes the sums of the squares of the two adjacent sides minus the square of the opposite side length and then divided by positive 2 adjacent 1 adjacent 2. It just makes it a little nicer to look at. I'll also point out that while I have not in class, and nor will I in this video, give a proof of why the law of cosines works, I've actually given you pictures here that will let you figure it out. Noticing that I've drawn in this dashed line H, I've created a couple of right triangles in both pictures, and that by drawing the line H, I've broken the length of the side opposite into two pieces, which I call little o1 and little o2. You can use right triangle trigonometry and the Pythagorean theorem in order to get the law of cosines from here. It takes a little ingenuity, but I'm confident you could do it if you want to. If not, feel free to come up and talk to me. Or don't, I guess, if you don't want to. In any case, since our next goal is to actually get through some problems, let's get through some problems, the first one of which is below. It's a little bit small, but we are apparently placing garden sprinkler heads. We know the distance between the garden sprinklers are going to be 5 feet, 7 feet, and 8 feet in order to get this triangular region, and we want to find the optimal sprinkler spray angles for these corners. You'll notice this means that we have 3 side lengths, but we don't have the angles between them, and that means that we can, in fact, use our law of cosines here. I'm going to begin by doing this a specific way. So the first thing I'm going to do is I'm going to label the angles at the corners. Then what I'm going to do is I'm going to label the sides. This will hopefully help us remember which sides are opposite which angles. And then finally, I'm going to point out, while solving for the first angle, which for me is just going to be A to keep things simple, that technically speaking, based upon what we did up above, I don't need to start writing everything out using the first formulation, the quote-unquote correct formulation of the law of cosines. I could skip to one of these formulas. The first time around, though, I'm going to write the equation just as the law of cosines originally appears, and then I will also show what it looks like when we rewrite it to solve for theta. Well, in our case, for A. After that, I will make things a little bit faster. Okay, so writing down the law of cosines with A being our angle, which means little a is the side opposite and B and C are the sides adjacent, we find, and if we now take exactly this equation and we solve it first for cosine of A, and then we solve for A itself by taking arc cosine of both sides, we wind up with the following. Now, I always recommend, at least in the beginning, that you go ahead and calculate what's inside the arc cosine before you actually finish your calculations. I think that just makes it a little easier to avoid mistakes. So I'm going to go ahead and do that now. It looks like if I start simplifying the fraction that I have inside, I should wind up with 11 over 14 once we simplify. So all I need to do now is take arc cosine of 11 over 14, and we're going to wind up with approximately 38 degrees if we round to the nearest whole degree. My calculator is actually showing something like 38.21, etc., if I take arc cosine of 11/14. I recommend that you store this exact value. We'll use it later towards the end. But for right now, we know our answer should be 38 degrees according to what the problem asks for. Let's go ahead and find B next. And this time, instead of doing all of the dancing around to find B using formulas, like the first formula going to the second formula, instead, I'm going to move directly to the formula for B. Here it goes. And now I'm going to go ahead and simplify it. I'll make a new line this time just to make things easier. Based upon my calculations, it appears we're going to be taking arc cosine of 1/2. I actually don't even need my calculator for that one. Arc cosine of 1/2 has got to be 60 degrees. Now all that remains is to find the angle C, but of course we don't need to use the law of cosines for this one. As long as you have stored the exact value for A, and for B as well, although that's a little bit easy in this particular case, we can simply note that C is going to be equal to 180 minus A minus B, and then we can approximate once we've done the exact calculation, which my calculator tells me is 81.786, etc., without rounding, but with rounding would be 82, approximately. 82 degrees. So apparently, the optimal angles from these corners are going to be 38 degrees, 60 degrees, and 82 degrees, and this completes the problem. Here's another exercise. This is actually a pretty common one to get. So we have two ships that are leaving the same port. One of them leaves at 1 p.m. and the second leaves at 3:30. The first ship sails at a bearing of south 37 degrees east at 18 miles per hour, and the second sails on a bearing of north 28 degrees east at 20 miles per hour, and we want to figure out how far apart they are at 8 p.m. This is one that requires a careful drawing, so the very first thing I'm going to do is I'm going to add in our cardinal directions. I'm going to put them right here, and I'm going to assume that the dock is here, right at the center. That just makes things much easier. So, Let's start out with just drawing the approximate lines we're going to need. So the first one is the ship A, which left at a bearing of south 37 degrees east. So in other words, it starts heading south and east, like so. And if you measure the angle from due south to our line, it becomes 37 degrees. Then we'll go ahead and draw the other ship, so that'd be ship B. And ship B sails at a bearing of north 28 degrees east. Okay, so that means if I start here, we travel north, but slightly to the east. Specifically, if we measure this angle right here, it turns out that is 28 degrees. All right, that gives us a little bit of angle information. We'll have to do some more in just a moment. Actually, why don't we go ahead and do that now? I think this is probably going to be the easiest part. So let's just look at, for example, our red angle here. You'll notice that if we pivoted from south to due east, we would be going through a 90-degree arc. But we're actually only looking at an angle inside the triangle we're going to make, because we certainly are going to make a triangle once we draw the line connecting the red and the blue points. Let's see, it looks like we're only going to be doing 90 minus a 37-degree rotation to go from our red line up here to due east. Okay, and it also looks like if we wanted to go from our blue line down to due east, we would be going through 90 minus 28 degrees. In other words, if I want to know what the total angle is here, since it's broken into the angle made by the blue ship and due east, and the angle made by the red ship and due east, I can simply add those values I get. So in my calculator, I'm going to put 90 minus 37 to represent the angle between the red ship and due east, and I'm going to add to that 90 minus 28, and it looks like we're getting 115 degrees. So let's go ahead and write that in here. 115 degrees. Then let's go ahead and connect these two dots. Sorry, I hesitated. I had to recollect my thoughts, which doesn't sound like a lot of stuff to do, but you'd be surprised sometimes. And it looks to me, as I'm gazing at this picture, like probably what should happen is I should be using Law of Cosines with SAS data. If I had the lengths of the blue and the red sides, and then this 115-degree angle, then finding the distance along this black dashed line would be easy. So what do I know that will give me the red line? Oh, well, ship A started at 1 p.m., and continued traveling until 8 p.m., which is when we try to measure distance. So that is going to be 7 hours. And it was traveling for 7 hours at 18 miles per hour. So if I do that multiplication, it appears that the length of the red side is 7 times 18, or 126 miles. Similarly, it looks to me like the blue ship B traveled from 3:30 until 8 o'clock, so that's going to be 4.5 hours. And for the whole time it was traveling at 20 miles per hour, so if I do 4.5 times 20, that would be 90 miles. And there we go. There is our SAS data. So now we just have to put this all into our calculators correctly, and we might as well go ahead and formulate this all correctly, with D representing the distance between the two boats. So let's put the formula in front of ourselves. Okay, excellent. That's what the formula looks like. So if I feed that to our calculator, we should be getting, and I'll go ahead and write down an exact answer here, 33,560.9821 8, and it just kind of keeps on going. That would be the exact answer for D squared, but of course we only want to know what D is, so we simply take the square root of that answer we just received, and we find out after taking the square root that if we were to round our answer to the nearest tenth of a mile, like we're being requested to do, it should be approximately 183.4 0.2 miles between the two ships. Now, we should also take time to mention something else that the law of cosines can do. If you start looking at the information that we've got here, you'll notice very quickly that even though it says to solve via the law of cosines, we're actually looking at a side-side angle triangle situation. And a drawing, since the angle here is 40 degrees, that should look something like this. When you see it this way, you may not think to yourself, I can use law of cosines at first, but let me add in one more piece of information. The unknown here is little c in this picture. So once I put in little c, suddenly I have an angle, two sides adjacent, and the side opposite. It just so happens that the angle, one of the two adjacent sides, and the side opposite were given information. So we technically can put this into the law of cosines. And if we do, just based on how I've set this up, A is opposite, B and C are going to be the adjacent sides, A is our angle, we should get a formula that looks like this, where I'm going to continue to write C in red to remind us that it is a variable. It's the unknown in this particular case. Everything else, even if it would be hard to calculate by hand, can be calculated. Okay, so now with the equation written this way, you'll notice suddenly I have an unknown squared and stuff times an unknown and then a constant being added. We could actually rewrite this equation if we wanted. We could bring everything over to the right-hand side of the equation, and we would get something that looks like this. Now, when you write it this way, it looks a little bit like a quadratic. In fact, there's a specific type of quadratic that this looks like, so I'm going to write the similar-looking equation in blue underneath. In the similar-looking equation, we would have 0 is equal to something times x squared plus something else times x plus a third something with no x attached to it. And in a situation like this, we could use the quadratic formula. So the quadratic formula then would be written as follows. We would have the negative of q. You'll notice here I'm using q instead of the standard a, b, and c, and that's because we have very rudely used a, b, and c in our triangle, so we've got to make do, plus or minus the square root of q squared minus 4 times p times r, and all of this should be divided by 2 times p. If you do this, you can figure out what x is, and we can do a very similar thing to figure out what c is, if c is possible. In this particular case, you'll notice that since it's just c squared, the coefficient on c would be 1. When I talk about q, I mean everything that is being multiplied by c, so negative 40 cosine of 40 degrees, and when I talk about r, I mean 300 here. Now, it may be tempting for you to look at this formula and go, yes, I've worked with this before, let me just go ahead and calculate, but there is something that we should note first. The stuff inside the square root here is called the discriminant, and while I won't go into the theory too much, the discriminant tells us whether or not we can even have any answers. If you recall from your college algebra days, if the inside of the square root, so in other words, the discriminant is negative, then we will get no answers because we are not permitted in this course to take the square roots of negatives. If the inside is 0, then the square root portion will disappear and we'll be left with negative q divided by 2p and get only one solution. That would correspond to us having a right triangle, actually. And then finally, the final option here would be if we find out that the inside is positive, at which point we simply have to calculate this fraction and then determine how many answers we can get from that. It's a lot of information to take in, but the important thing to understand is before I start, I should go ahead and check the discriminant for my information and see what's happening. So if I check the discriminant, so I'm just going to write DISCR, just to remind myself that's what I'm doing here. What would I be writing down? Well, B is all, or excuse me, I'm getting used to those old labels too. Let's use the new labels. Q means all of this, so negative 40 cosine of 40 degrees. squared minus 4 times p, which in our case is 1, times c, which in this case, or I'm sorry, r, which in this case is 300. And if I do that and feed it into my calculator, well, I'm getting some hideous number, but it's negative. Uh-oh, the inside of the square root is negative. So as we talked about just a few minutes ago, there must be no triangles. So that ends the problem. If you were going to use the law of sines in this case, what you would have to do is calculate h. And since I haven't put it in the picture yet, let me go ahead and indicate where it would be. We would calculate h, and what we would wind up finding out is that h is longer than a, the side opposite, and that is also another way of saying there are no triangles. Let's go ahead and do another one. We should look at the work it takes to do one of these sorts of problems. So we're going to solve via the law of cosines, and what we're going to solve involves very similar information to before. However, I'm going to go ahead and make an observation. If we were doing the law of sines in this case, and I guess I should draw the picture as I'm saying this, you might notice that the length of the side opposite is greater than the length of the side adjacent. When doing law of sines, that was a good indicator we were in what we call case 4. We don't have to calculate h at all. We simply notice the length of the side opposite is greater than the length of the side adjacent, and so there should only be one triangle, and it would look more or less like the one I'm drawing here. However, we can't use the law of sines here. We're using the law of cosines, so let's just use the law of sines info we're getting as a prediction. What it's telling us is to expect that there is going to be a triangle here. However, there's only going to be one. There won't be more than one. If you want to figure out how to do the more than one triangle case, it's going to look exactly like the work we're doing now. There will be only one minor difference, and I'll show you where that difference is. For now, let's go ahead and employ the law of cosines like we did before. Remember, we're going to start with b and c, the unknown, as our adjacent sides, a as our angle, and little a as the side opposite, which gives us the following equation. 30 squared is equal to 24 squared plus the unknown c squared minus 48 times c times cosine of 36 degrees. I also was sneaky and changed the color, but I want to do that so that way we can work in a color that clearly distinguishes itself from our base information, and which also makes sure we know what is the unknown in this case. I'll go ahead now and I will recollect things so that way we have our quadratic equation. And now I'll go ahead and compare it once again with the sorts of equations we're interested in. This time I'll use x as the variable. Remember, I'm just comparing my two equations. That's why I'm making my x's blue, just like I made my c's blue. And it leads us to two equations we'll need. The quadratic equation, I'll go ahead and make sure that it is c equals here. So that way we see that we're still solving for the unknown side c. And then, from this equation, or if you want just from knowing what it looks like, we get our discriminant, which, if we feed it into our calculator, gives us a number which is positive. Okay, so unlike last time, and this aligns with our guess, we should get some kind of answer. It might be a little bit ugly because the number I'm getting right now is pretty ugly, but we'll see how things goes. For right now, let's just go ahead and simplify the equation that we have for little c. You know what? These are such ugly numbers. Let's just go ahead and do the calculations. I'm going to put into my calculator what I see here. So if I do the first option, which would be, well, I'll go ahead and note this right now. Since we have the negative of a negative, that means we're talking about a positive 48 cosine 36. So if in between the 48 cosine of 36 degrees and this ugly square root, I put the minus sign, I end up getting something that looks approximately like negative 7.059. Actually, I'll just go ahead and make this exact. That way I can keep the equal sign I put there. And we know this is going to be a bad answer. We know it's a bad answer because we know that C is a length in a triangle, so how can we have a negative side length? Okay, that leads us to the case where between the 48 cosine 36 and the square root, we have a positive sign. And if I do that, it looks like I'm going to get 45.8927, and it just kind of keeps on going. Now, of the two answers I produced, this is the only one that makes any sense. So I'm just going to go ahead and say this is the only side length I could possibly have for C. That means we have an approximate value for C, which I will store in my calculator, and now we can use it to start solving for the remaining sides. But let me make some extra room first. Okie dokie. That means now we've got to solve for at least one more angle using the law of cosines, and I've chosen B. Let's go ahead and do that one quickly. Since C is a little bit ugly, I'm going to go ahead and refer to the memory on my calculator to do this calculation. And if we do that, we should get, and I think we'll go ahead and round to 2 decimal places, approximately 28.05 degrees. I've recorded the exact value in my calculator, because now I'm going to find C, and to find C, of course, what we're going to do is say C is equal to 180 minus A minus B, which gives us approximately 115.95 degrees. Alrighty, now as I mentioned, if you wound up with a triangle that had, well, let's say a collection of SSA data that allowed for more than one triangle, that's the better way to say it than what I was going to say before, then when you get down to the step here where we calculate little c, you'd find out that both of the values that we get were okay, and then we would just have to do the same calculations we did down below for both of those sides c. In our case, we didn't need to do that, and you'll notice I added in one extra tiny detail by rounding little c to 2 decimal places. There is one more topic we should cover in this video, and that is something called Heron's formula for SSS triangle data. So if I'm given a triangle, and I'm given the lengths of the 3 sides as little a, little b, and little c, then I can find the area. It's denoted by k, once again, for some reason, and it is the square root of s times s minus a times s minus b times s minus c, and in this case, s represents something called the semi-perimeter. It's what happens when you add all the side lengths together and divide by 2. There is a proof for this in the book, but I'm not going to go ahead and do it. In my opinion, it makes the most sense to actually show you Heron's formula being used, which might be a harder task than it sounds like at first glance, since apparently I can't say the word formula. So we're going to go ahead and do a problem from the book. It will be a word problem, and it should be up on your screen in 1 second. Reading through this problem pretty quickly, we have a triangular lot with known side lengths. We'll get to that in just a second. We know how much we should be selling our lot for per acre. So what we need to do is figure out from this what the area is of our triangle so that we can convert that into acres, square acres really, and then what we should do, oh, I suppose it would just be acres, my bad. We convert square feet, just based on what we have here, into acres, and then we convert from acres into dollars. So let's go ahead and just roughly sketch out this picture and then follow through with Heron's formula. And we can go ahead and assign lengths. It doesn't really matter which side is which length in this picture. We just have to make sure that we label them and we know where they are. So let's see, here's 250, I'll say, and I'll say this one is 274, and that makes C 400 feet. Now, if you remember, in order to use Heron's formula, we need the semi-perimeter first. So let's go ahead and just fill in the semi-perimeter formula. Okay, with the semi-perimeter in front of us, written via the formula that we have up above, it looks to me like, from my calculator, we should be getting exactly Oh, shoot. Come on, calculator. Don't play games with me. 462. And this leads us down below to be able to calculate k. If we follow the formula, it appears that we'll have 462 times 462 minus 250 times 462 minus 274 times 462 minus 400. Takes up a lot of space, but it's not a hard calculation, and it's one that I'm going to feed directly to my calculator. And the exact answer I'm getting is 33,788.0935, and so on and so forth. This is one of those variables I'm going to store to my calculator. Okay, we now know the area of the lot, and based on what we said before, since an acre measures area, it's square feet, or rather, each acre is worth 43,560 square feet, we can figure out the number of acres by simply taking the answer we got a second ago and dividing by 43,560. Do this in your calculator, and you're going to wind up getting again, I'm going to be using exact answers for right now, 0.7756, and then it keeps on going. But I want to get dollar value, so I'm simply going to take the number of acres I've got here and multiply it by $1 million per square acre. And if I multiply by 1 million, I wind up with 775,667 let's round it to 2 decimal places, $90. And again, that's what happens if I take this value and I multiply by 1 million. Okay, that should be everything that we need to cover in this video, guys. Fantastic job. We got through it in record time. Remember to practice your problems in the law of cosines. Remember what I've said in previous videos and announcements, which is use the law of cosines for law of cosines problems. Use the law of sines for sines problems. Don't intermix them yet, at least not till the next video comes out. And until then, everybody, happy math.